In this video, we can discuss about the program flow control instructions related to 8051 microcontroller, and in which we have the jump instructions and call instructions. Okay, and the jump instruction we can further divide it into unconditional jump instructions and conditional jump instructions. And the unconditional jump instructions are long jump, absolute jump and short jump instructions. The long jump instruction, the syntax or the representation for or the keyword for long jump instruction is LJMP and is a 3-byte instruction. The first byte represents the opcode and the second and third byte represents the 16-bit address of the target location. The 2-byte target address is to allow a jump to any memory location from 000 to FFFFH. That means long jump ranges in a 64 KB memory space. This one indicate the various byte addresses of different bytes in a 64 KB memory. So long jump allows the jump anywhere inside a 64 KB memory. And it's a 3-byte instruction, and the first byte indicates the opcode and the remaining 2 bytes indicate the 16-bit target address. And this is the keyword for long jump, that is LJMP. Similarly, we have another unconditional jump, that is the absolute jump instruction, and its representation AJMP. This absolute jump, this indicate a jump within a 2 KB of memory space, a 2 KB in a memory space. Okay, so this jump indicate a jump to a next address given by 3 lower bits of the first byte of the instruction plus the second byte, total 11 bits. Least 11 bits form the address of the target location and the remaining higher 5 bits form the opcode part. So this is actually a 3-byte instruction in which the first 5 bits, higher 5 bits form the opcode and the remaining 11 bits form the operand address. 11-bit operand address. The 11-bit actually indicate using this a jump instruction, it can jump inside a 2 KB of memory space. And next is a sjump instruction, SJMP. This means a short jump instruction. This one is actually a 2-byte instruction where the first byte is the opcode and the second byte is the relative address of the target location. In these 3 cases, the jump is relative jump. That means from the current location, it can jump in a 64 KB memory or in a 2 KB memory, or here in case of a 256 bytes of memory. Okay, so this SJMP support a 256 bytes jump. The relative address ranging from 00 to FFH, which is divided into forward and backward jump here. That means this short jump permit a jump 128 bytes backward and 127 bytes forward. As a total 256 bytes it can consider for jump with regarding or with related to the current location. Okay, so for unconditional jump instruction, we have 3 categories: the long jump, absolute and short jump. And long jump and absolute jump are 3-byte instruction, and long jump permit a jump anywhere in the 64 KB of memory, and a jump permit a jump inside a 2 KB of memory space. And for long jump, the first 1 byte indicates the opcode and the remaining 2 bytes indicate the 16 bits of memory address for the target location. And in case of a jump, the first higher 5 bits form the opcode part and the remaining 11 least bits form the address of the target location. And in case of short jump, it's only a 2-byte instruction. The first byte is the opcode and the second byte is the operand address, for the target location, and it permit forward and backward jump, and forward 127 bytes. It can jump to a maximum of 128 bytes forward and 128 bytes backward. Now we can consider various conditional short relative jumps of 8051. This JN set with a relative address of the target location means jump to a relative address if the accumulator content is non-zero. And similarly, J set a relative address means jump to a relative address given here if content of A is 0. J and C with a relative address means jump to a relative address if the carry flag is not 1. That means if no carry occurs regarding the previous operation, then it perform a jump. If no carry exists, then it perform a jump to a relative address given here. JC means it jump to a relative address given here if the carry equal to 1. JB bit comma relative address. This means jump to a relative address if the addressed bit is equal to 1. This one indicate the bit address of a particular memory bit. So if that particular bit location having value 1, it perform a jump to this relative address given here. This one is just the opposite, that is jump not bit. That means the given bit address position having a value 0, then it perform a relative jump to a given relative address here. This one JBC bit comma relative address means jump to a relative address if the addressed bit is in set form and reset carry. That means after jump, make the carry flag equal to 0, and whenever it perform a jump operation, if the given bit address location having value 1, then it perform a jump and make the carry flag equal to 0. So these are indicating short relative jump operations or instructions. Now we can consider some special case for this jump instruction, that is decrement conditional jump. That means DJ and set, decrement and jump, and if it is non-zero. Okay, that means here we have a register content comma a relative address, then decrement the register content by 1 and jump to the given relative address location after decrement this register content if it is not equal to 0. Okay, first decrement the content of this given register by 1 and check if it is equal to 0 or not. If it is not equal to 0, and it perform a relative jump to a given address location of the target memory location. Here it is DJ set direct comma REL. That means exactly like this, but the content is given as a direct memory content here. So decrement the value at that direct memory location by 1 and check if it is equal to 0 or not. If it is not equal to 0, then jump to the given relative address position. Okay, so this indicate the decrement and jump based on the condition, and the condition is the decremented value of the register or this direct memory location is not equal to 0. Okay, so next jump after comparison. So CJNE a immediate data comma a relative address means compare the content of accumulator with the immediate data and jump if they are not equal. Jump if not equal. Okay, so whatever values we need to compare the content of accumulator with a given immediate data. If they are not equal, then perform a jump to the given relative location. CJNE compare and jump if not equal. That means here instead of A, given a general purpose register with an immediate data. So the content of register is compared with the immediate data, and if they are not equal, then jump to the given relative address. Okay, so another syntax here, instead of the immediate data, here it gives the address of a direct address of a operand value. So compare the memory content with the accumulator content. If they are not equal, then perform a relative jump to a given relative address location. Okay, next one, CJNE at the rate RI comma data comma relative address. This one indicate actually here also we need a comma separation. Okay, so this is a syntax mistakes. CJNE A comma immediate data, RN comma immediate data, A comma direct. Okay, so similarly this one indicate an indexed or indirect method of instruction representation. Here the content of memory location and the memory address is represented or pointed by RI register, particular register, and that content is compared with an immediate data. Here we need an hash symbol, immediate data. If they are not equal, it perform a jump to a given relative location. Okay, so this CJNE means compare and jump if the operands are not equal. So here we have three operand parts, two for comparison and third indicate the relative location of the or the location to which we need to jump after comparison. Okay. Next we have the call instructions. Okay, so the call instruction, call to subroutine instruction, comes under this program flow control instruction, and they are unconditional. Okay, so 8051 CPU saves on a call the return address onto the stack top. Okay, the return address is first pushed onto the stack, and also the special function register which are expected to be changed on the calling subroutine inside the subroutine body must be pushed onto the stack, and they are popped before the last return instruction from the subroutine. Okay, so the stored special or pushed special function registers as well as the return address first port back into its exact location before transferring the control back from the subroutine body to the main program. Okay, so for more clarity, consider one example. Assume before calling a subroutine, the stack pointer having or storing the value 30h. So this is a particular memory byte address which is stored in stack pointer, because this indicates that the stack top currently pointing to this byte address 30h. Okay, and assume the program counter PC currently holding the value 20F0H. Right? So now we can consider. So consider this one. So this one indicate the internal RAM space, and from this 80H to FFH of our RAM space form the special function register area, in which the 81st byte indicate the starting or direct address of our stack pointer. Keep in mind, the 81st byte of our memory indicate the stack pointer register. So based on the condition given, initially the stack pointer or the 81st byte holding the value 30h. That means the stack pointer now pointing to this particular byte. Okay, so this is the case of initial stack representation before calling a subroutine. Okay, and also the PC is holding a return address this 20F0 based on the given condition. Right? So now consider after calling the routine. Okay, so after calling a routine, we need to transfer the control from the main program to the subroutine body. So before transferring the routine, we need to increment the stack pointer content by 1. So initially the stack pointer is pointing to this 30H here. So increment that 30H by 1 and pointing now the stack pointer here in 31H. Now we can push the lower byte of PC to here. Okay, again increment the stack pointer by 1 and SP now pointing to this 32H. Here we can store the higher byte of PC. Okay, so after these two push operation, now the 81th byte or the stack pointer pointing to 32H. Now we can load this program counter with the return address, the target address. That target address actually pointing to the starting of the subroutine body. Now we can load this PC with the starting address of the subroutine body and transfer control to the subroutine body. So inside the subroutine body, after executing this return instruction, what will happen? After executing this return instruction from the subroutine body, we need to pop back the post content onto its exact location. So directly check the current status of stack pointer, that is the 81th bit of our internal RAM space, which currently holding the address 32H. So move to 32H and pop this top value and place into its exact location. This is actually the value pushed from the higher byte of PC. So pop it back and place into the higher byte of PC. Then decrement the stack pointer by 1. Now it pointing to 31H. Again pop the stack top, that is F0H, and place into the exact position, that is lower byte of PC. Again decrement the stack pointer by 1. So now after completing this pop operation, the stack pointer pointing to the initial 30H. Now the return address is loaded in this PC. Now we can move back or go back to the main program up to a location which is now available in PC. So from that point, the main program can resume its execution. So this is the actual working of a call instruction, okay, with the help of stack and stack pointer. Okay. Here for supporting such subroutine call instruction, we have two types of call instruction, that is lcall and acall instruction. Lcall means a long call instruction. That means this is a 3-byte instruction. Okay, lcall, that means the main program in which a subroutine is calling and the called subroutine, both code may be present anywhere in the 64 KB of memory. That is why such type of calling indicate lcall instruction. Using lcall instruction, we can represent such instruction. That means the calling main program body and the called subroutine body present anywhere inside the 64 KB of memory, right? So this is a 3-byte instruction in which the first byte indicate the lcall opcode itself, and the remaining 2 bytes form the 16-bit target address. The target address actually indicate the start of the subroutine body. So this is a syntax of lcall instruction. Lcall space the target address. The target address is a 16-bit information indicating the start of the subroutine body. So while executing this, what will happen? The program counter is incremented by 3. Because this is a 3-byte instruction. In order to get the next instruction address, the next instruction address actually form the return address. So we need to increment current program counter value by 3. Then increment the stack pointer by 1 and load the stack top with the lower byte of PC. Again increment the stack pointer by 1 and load the higher byte of program counter onto the stack top. Next, we can load the program counter with the target address, 16-bit target address of the subroutine body, which is available here in this instruction. Okay, so this is the case of lcall instruction. Next, we have the A call instruction, absolute call instruction. That means the calling main program body and the corresponding subroutine body must be present inside a 2 KB of memory space. Inside 2 KB. So this A call is a 2-byte instruction in which the higher 5 bits form the opcode. That is, the opcode corresponding to A call is present or represented using the first 5 bits of our entire 2-byte instruction, and the least 11 bits form the target address of the target address. That means the starting address of the subroutine body. Okay, so while calling such an a call instruction, while executing such an a call instruction, what will happen? This is actually a 2-byte instruction. So increment first the program counter by 2. So after incrementing by this 2, because this is a 2-byte instruction, so after incrementing this current value of program counter by 2, we get the next instruction address of main program. That particular address form the return address to the main program. So increment PC by 2, then increment stack pointer by 1, and to that stack top location load the lower byte of PC. Again increment stack pointer by 1, and to that location load the higher byte of PC. Now the PC become completely free for loading the target address. So in which we can load the 11 bits of target address and is loaded from least bit position to towards MSB. Okay, so the target address is available directly from this instruction, A call instruction itself. So this is the working of this A call instruction. Now the PC is loaded with the target address, so we can directly transfer control to the subroutine body. Next is another type of instruction, that is the interrupt flow control instruction. So the interrupt flow control instruction is actually RETI. That means regarding to an interrupt call or interrupt request, whenever the processor is ready to execute an interrupt request, transfer the control to the interrupt service routine. At the end of the interrupt service routine, we have a special instruction RETI, return from interrupt service routine. Okay, so the syntax is RETI instead of RET. RET is actually used in case of a subroutine call. Inside the subroutine body, we have the RET instruction at the end indicate we need to return from the subroutine body to the main program. Here in case of interrupt request, inside the interrupt service routine at the end we have this RETI instruction. While executing this instruction, it indicates the transfer control from the interrupt service routine back to the suspended main program. Okay, so all these, now we have completed all different types of instructions of 8051. Okay, thank you.